Very happy to be here. Thank you for the invitation. Rafael told me you're all experts in nuclear physics, so I hope you will shape up. This will be a complicated talk. No, he said, go really easy. There are very few experts on nuclear physics. So I will try to give you an impression of what it's like to work in this field of nuclear astrophysics. So just to give you an impression, our group, you know what the size of the group is. There are 3 of us in this laboratory that I will explain to you. So there's Art Champagne, Richard Longland, myself. We have 2 postdocs, Caleb Marshall, Thanasis Psaltis. We have about 10 graduate students, and then we have a group of undergraduate students who work with us. So let's start with a cosmic history on one slide. You've seen this many times before, but I will sort of explain this in terms of the nuclear physics. So 13.7 billion years ago, there was a Big Bang. Everything started with that. And then 200 seconds after the Big Bang, the first nuclear reactions occur. And we'll explain a little more, what kind of nuclear reactions. Then 300,000 years after the Big Bang, the nuclei and electrons combine, they form atoms. The universe becomes transferred to photons, and that is where you've seen, I will explain this in more detail, the cosmic microwave background radiation, the baby picture of the universe. But remember that we have an earlier probe, namely what's happening 200 seconds, compare 200 seconds to 300,000 years. I'll explain this in more detail. Then the first stars form 300 million years after the Big Bang. 1 billion years after the Big Bang, galaxies form, and then the solar system formed 9 billion years later. And then here we are, November 27th, 13.7 billion years later. Nuclear physics. So what's happening here around between 100 and 30 seconds after the Big Bang, we call this Big Bang nucleosynthesis. So for the first time, nuclei, that means protons and neutrons combine, they form atomic nuclei. And what's happening here in terms of element synthesis, the Big Bang forms hydrogen, helium, and lithium, and nothing else. And then there's a big gap. And
I've got a talk.
Nuclear reactions occur again inside stars. So after 300 million years up to today. So this is where nuclear reactions occur. When you see a star, the light was produced, the energy derives from nuclear reactions in the interior of the star. So all of these cosmic phenomena that you're hearing about, supernovae, classical novae, and so on, they only happen because there's nuclear reactions going on. In other words, without understanding the nuclear physics, you will never understand these phenomena. I will focus in this talk on explosions. So we'll tell you a little bit about Big Bang nucleosynthesis, classical novae, thermonuclear supernovae, and I will not talk as much about core collapse supernovae and kilonovae. If you have any questions, please feel free to interrupt. So we're made of stardust. There are 19 elements that are essential for life as we know it. And I will explain to you where these are coming from. I mean, all of these elements are made in stars. I will focus only on the 19 elements that are essential for life. So hydrogen, already mentioned, is made in the Big Bang. So almost all of the helium in the universe today was also made in the Big Bang. But helium is not essential for life. So I'm only showing the ones that are essential for life. So hydrogen is made in the Big Bang. The ones in blue, half of the carbon and half the nitrogen in your bodies, and molybdenum, which is essential for some enzymes, they're made in asymptotic giant branch stars. So these are stars in an advanced stage of evolution. The sun will become an AGB star eventually. And these AGB stars, they produce these beautiful planetary nebulae. So this is an image of the famous Cat's Eye Nebula. Then, going on, everything in orange here, so the oxygen we breathe, the phosphorus, magnesium, sodium, is made in massive stars. When I say massive stars, these are not being fused in the sun. The sun is not massive enough. With massive, I mean a star beyond 10 solar masses. before it will explode, something bad will happen to it, it will produce these kind of elements in orange here. This is an image of Betelgeuse in the constellation Orion, which is a famous example for a red supergiant. These massive stars then eventually collapse at the end of their evolution, and they explode as a type 2 supernova. And here's a famous image of the Crab Nebula that was discovered in the year 1054. And these type of explosions produce half of the iron in our blood cells, half the manganese, all of the chlorine, all of the calcium in our bones. Then going on in green, iodine, that is essential for our thyroids to function, and half the selenium is made in what we call the R process. Not entirely clear where that is happening. It's either happening in colliding neutron stars or also in these type 2 supernovae. Then finally, everything in purple, half of the iron in our blood cells, half the manganese, half the copper and zinc is made in another type of supernova explosion. This is supernova, this is supernova, this is type 2, this is completely different size. I will tell you a little bit more about what these type 1a supernovae are. This is a famous image of a type 1a supernova, Tychos supernova. So, yeah, this is the origin of the 19 elements that are essential for life. Of course, if you want to know where all these other elements are being made, you have one of your colleagues here, Chiaki Kobayashi, is a world expert in this. She knows this stuff much better than I am. So I don't know what I'm talking about here. So she knows all the details because she's an expert in galactic chemical evolution. So more than 10 years ago, I teamed up with a friend and collaborator of mine, Jordi José from the University of Barcelona, and we wrote a review on nuclear astrophysics. There are very few review papers on nuclear astrophysics. Most of them that were published after, they're on aspects of nuclear, hydrogen burning, interstellar evolution in nuclear physics. But this was all of nuclear astrophysics. And I'm telling you this because what we did, we ended this review with 15 key questions in our field. And I will not read the questions here. I just want to tell you, people sometimes say to me, oh, yeah, you're interested in how stars generate energy and where the elements are coming from. But nuclear astrophysics is a much richer field. And what I want you to take away from this is there are many different connections that we make between other subfields of astronomy. So, for example, here, nuclear astrophysics, the key question is, why do predictions of helioseismology disagree with those of the standard solar model? It goes on. It involves the Big Bang. It involves gamma ray astronomy, all the way to galactic cosmic rays. So picture nuclear astrophysics as a field that makes connections to many different subfields of astronomy. Everywhere where you need to know the nuclear physics, and nuclear physics drives a lot of these phenomena. Okay. Are you guys ready for nuclear physics? This is the hardcore of the talk. So what we need, I just want to explain two concepts to you. And then one is what do we measure in the lab? We measure cross-section. What is a cross-section? This is a historic definition. But here you have two nuclei that fuse. This is a proton, and this is another atomic nucleus. Can be anything. So in red are protons, in gray are neutrons, and they need to fuse. We call that a nuclear reaction. In the laboratory, we measure the cross-section, which is defined as the number of nuclear reactions that occur per time, divided by how many incident projectiles you have, and also divided by the number of target nuclei you have. That's the cross-section. So let's have a look at a cross-section. This is the cross-section for this reaction. In nuclear physics, we use this particular notation. You see that there's a comma here. Everything on the left side of the comma is what you have before the reaction. So before the reaction, you have an oxygen 16 nucleus and a proton. And everything on the right side of the comma is what you have after the fusion occurred. So fluorine 17, if you combine these two things, and an outgoing gamma ray. So this is the cross-section on a logarithmic scale versus the kinetic energy in the system between these two interacting nuclei. And you see something very interesting. At low energies, it drops like a rock. So in other words, it's easy to measure this nuclear reaction at 2 MeV here. You measure something. But if you want to measure where the star burns, which is where you have no data right here, then it's very difficult. Your signal will be very small. Why? Because of quantum mechanical tunneling. This is a charged projectile and a charged target. They don't want to fuse together. They only fuse because of quantum mechanical tunneling. And as we learn in our undergraduate quantum mechanics, this quantum mechanical tunneling probability depends strongly on energy. And if you do the math in your undergraduate quantum class, then you usually find this tunneling probability, and it's given, if you remember, by the gamma factor, e to the minus 2 pi eta. I don't know how many of you remember this. The eta is called the Sommerfeld parameter, all technical stuff, and this depends on the charges of the interacting nuclei and some constants. The important physics is the energy. The energy occurs square root 1 over the square root of the energy, and it appears in the exponent. So when people say, oh yeah, when you lower the energy, the cross-section drops exponentially, that's not true. It's the logarithmic scale. Exponentially means it would be a straight line. It drops much stronger than exponentially because the energy dependence is e to the minus 1 over the square root of e. So this is very difficult to deal with. We're mostly interested here in this energy range where this drops like a rock. So we really find the cross-section into a quantity we call the astrophysical S factor. What we do, we take the cross-section and we divide out what we know. We can calculate the tunneling probability exactly. It's very easy. And we divide out what we know, and what's left over is what we do not know. That's the astrophysical S factor, and it looks like this, same data. Now you see this is a logarithmic scale covering 7 orders of magnitude, and this is a linear scale, and you see how this fusion cross-section, if you redefine it, varies much, much less. And this is a key concept in our field, because if the star burns here where there are no data, you probably would feel comfortable extrapolating this curve somehow with a fancy model. But here, it's very, very difficult. It's impossible to see anything. So the other concept that is key is what you need to model stars, explosions, stellar evolution, so on, is called the thermonuclear reaction rate. The thermonuclear reaction rate is the number of nuclear reactions that occur in the stellar plasma per unit time, per unit volume. That's what you need. Now, I told you if you want to measure this cross-section at 2 MeV, you do the measurement, but that's not how stellar plasmas work. In the stellar plasma, you have a distribution of kinetic energies, and you need to average the cross-section over this distribution of kinetic energies. In almost all cases, the distribution of relative kinetic energies is given by a Maxwell-Boltzmann distribution. In almost all cases. So then the reaction rate can be very easily calculated by an integral of the cross-section and the Maxwell-Boltzmann distribution. That confuses people sometimes. They say to me, oh, so you do measurements, you have a fusion reactor and you do the, no, we don't do anything like that. It's impossible to do right now. We have ion accelerators. All we do is measure cross-section, and once we have the cross-section, it's a very simple matter to calculate the thermonuclear reaction. That is the number we then plug into the stellar simulations. Do you have any questions so far? Okay, if I go too fast, just say, hey, that's just enough. It's just way too much information. So yeah, if you want to see the gory details, then this is a book that was published a couple of years ago, and sort of this is on a graduate student level. Okay, so schematically, this what you want to try to do is looks like this. You have a cosmic phenomenon. This can be observed gamma rays or a supernova explosion. It has observables. So say you want to study, you observe a supernova. The observable is a light curve, gamma rays, and you see elements in the ejecta. And you want to understand that. Well, what do? You build a model on the computer, and then you have input A, B, C, and then you make predictions, and then you compare the prediction with the observables. And only if you get matches, then you have some hope that what you simulate in the computer has some sort of relationship to reality. So let's focus on the nuclear physics. All these phenomena that I explained to you, you cannot understand without understanding the nuclear physics input. So what we maintain a very large nuclear physics library. What this library has, it has all these nuclear reaction rates for all sorts of nuclear reactions, 10,000s of different nuclear reactions that combine different nuclei. So we put that as input into our simulations, our model. And then we can also, if we know, and we do know what the uncertainties in our reaction rates are, because we can quantify the probability density functions, we can perform a Monte Carlo simulation and run the model many times. And so we perform Monte Carlo sensitivity studies. So by doing that, we can identify which reactions are the most important ones and which reactions need to be measured in the laboratory. So if you have a supernova explosion and there are 20,000 different reactions in your network, you don't need to measure 20,000 different reactions. You need to focus, you need to find out which are the most important ones for this particular observable. So then we can perform informed experiments in the laboratory. And once we take the data, we need to analyze the data with smart statistical methods. And that information feeds back into our library. And then when we go around the cycle, then hopefully we improve things and we learn something in the process. There are very few other groups who do all four things. We do all four things. We do measurements, we have developed statistical methods, and we do these Monte Carlo reaction network studies and so on. So, okay, let's start with the Big Bang. This is what I was alluding to earlier to you. This is the baby picture of the universe. 380,000 years after the Big Bang, when atomic nuclei and electrons combine, the universe becomes transparent. And this is the famous Planck satellite picture. And what you're seeing here, these different colors, are fluctuations in the microwave background radiation. And they're on the level of microkelvin. And this has been very important, the analysis of this. This shows you, tells you where at that time mass concentrated and will later evolve into galaxy clusters, and where there were voids, there's no matter. But the analysis of this tells us very important quantities. It tells us the precise value for the age of the universe. 13.7 billion years with a very small uncertainty. It tells us what the dark matter content is in the universe, the dark energy content, and so on. So this kind of study of the cosmic microwave background radiation that put cosmology into the realm of a precision science. Now, remember what I said earlier. Oh, and for this work, John Mather and George Smoot, they were the first. They obtained the Nobel Prize in 2006. Remember what I said earlier. I said that there's a much earlier probe, 380,000 years, 200 seconds after the Big Bang. This is where Big Bang nucleosynthesis occurs. So I told you that tens of thousands of reactions in supernova explosion. Big Bang nucleosynthesis is very simple in terms of nuclear physics. There are only 12 reactions. They're listed here. And they're shown here in a network. We can think of proton number increases this way. So you have different elements. This would be hydrogen, helium, lithium, beryllium. And the neutron number, so different isotopes, that they change in the x direction. So proton, deuterium, tritium, there's helium-3, helium-4. So this figure is from a paper that Raphael first authored, we published in 2019. And just to tell you what we measured in our laboratory are these links here. So it just tells you, if you want to study Big Bang nucleosynthesis in the laboratory, it's not that there are a lot of missing data. it's more like that a lot of people have measured these reactions, but how do we analyze them properly? The key is, how do we obtain realistic uncertainties? So the first time that Bayesian statistics was applied to thermonuclear reaction rates was in this paper in 2016. We're very proud of this paper. And Bayesian, a lot of different subfields are using Bayesian methods, but I can tell you that low-energy nuclear physics is very conservative in terms of statistics. And this old saying of Lord Rutherford that goes like, well, if you need statistics, you're in trouble. You really should be doing a better measurement. This is how people think in low-energy nuclear physics. And what we then did, we just applied these techniques to thermonuclear reaction rates, and that was a game changer. And now many other groups have adopted this. And so after this, we did a number of follow-up papers. What we did really in 2016, we picked the simplest cases. And then we wanted to go on to more complicated cases where we're stuck. And that's when I'm stuck, what I do, I then just work with other people. And that's why we hired Raphael. And then that's how we develop these additional techniques. So here's an example. This is a paper we published 2 years ago. Joe Moscoso was a graded student of mine. So this is the S factor. Remember, the cross-section drops like a rock, but this is the S factor. We removed the quantum mechanical tunneling probability. You can see there are lots of data published between 1955 and 2021. It's not that data are missing. It makes no sense for us to really measure that. Some of these data were measured in our laboratory. It's a matter of how do you analyze these data? Now, anybody can put a chi-square fit to these data, but then what we want to know, what are realistic uncertainties? That's where the Bayesian techniques come in. What you see here in this magnifying view of Bayesian, the credible S factor fits that we obtain here, and we can integrate each of these to obtain the thermonuclear reaction rate. So you end up, very importantly, with a histogram, a probability density function for the reaction rate. This is the reaction rate on the x-axis, probability on the y-axis. This then precisely quantifies your uncertainty in the reaction rate. That's exactly what you need for these kind of simulations. So before I will show you the results, I want to talk a little bit about the temperature and density evolution during Big Bang nucleosynthesis. So 75% of the hydrogen and 25% about by mass of helium originated in the Big Bang. And you have time after the Big Bang on the x-axis, the temperature on the y-axis on a logarithmic scale. This is 1 second after the Big Bang. No nuclear reactions happen here because all you have is protons and neutrons. If they combine to form deuterium, the temperature is so high here, it will immediately disintegrate again. So you need to wait. The nucleosynthesis has to wait until the universe cools, where protons and neutrons can combine to deuterium. Deuterium can combine with another proton to something else according to the network I showed you before. So Big Bang nucleosynthesis occurs in this range here, between 100 and say 1,000 seconds. And then beyond that, the universe is cooled too much and there's just not enough energy in the system anymore so that quantum mechanical tunneling can occur. So if I would have asked you, what do you think is the temperature during Big Bang nucleosynthesis? Most of you would have guessed a very large number. So you can see it's about 1 billion Kelvin. If I would have asked you the same about the density shown here, probably very few would have guessed what the density is during Big Bang nucleosynthesis. As you can see, it's 10 to the -5 gram per cubic centimeter. Let's put this in perspective. The density of air in this room here that we breathe is 10 to the -3 gram per cubic centimeter. So Big Bang nucleosynthesis occurs at a density, a factor of 100 less than the density of air in this room. So we did these Bayesian analyses of reaction rates for the key reactions in Big Bang nucleosynthesis. And in this paper published a few years ago, I teamed up with a colleague of mine from Orsay, Alain Cook. And these are the results. In this research field, the primordial abundances, they're always reported in this way. The mass fraction for helium-4, and then deuterium over hydrogen, helium-3 over hydrogen, lithium-7 over hydrogen. It's just for historical reasons. But this is all we observe. And now we need to see. Helium-4 is not so interesting. Oh, so in orange, in red here, is the observational range, the best observations today. And in blue are our simulations of the nucleosynthesis with our very reliable thermonuclear reaction rates. And you can see, oh, the simulations, they're right in the observed range. Great. But this is not very interesting because the observational uncertainty is so large. You cannot really do precision cosmology this way. And of course, people, experts in the field, they want to reduce the uncertainty, the error bar in the observations. Helium-3 is not very interesting either because all we have managed so far is measure an upper limit in helium-3 of hydrogen. And yeah, our simulated value is below the upper limit. Great, but that's all you can say. Now, this is very interesting. Observation and simulation. This is a factor of 3 difference. This is the famous cosmological lithium problem that nobody understands. What we did in this paper is we applied a genetic algorithm to see if some combination of reaction rates, those 12 that I showed you before, maybe can give rise to, can solve this problem and can move the simulation distribution of this abundance into the observed range, but it can't. Nobody understands this problem here. We don't have it. There's some ideas for solutions, but this is one of the open big questions. But this was known. This is we didn't discover it in this paper here. This was, many people have seen this before. They haven't used, I think, as reliable reaction rates, but this problem was known. What we discovered, very interestingly here, is deuterium. This was not known before. So we may have a cosmological deuterium problem in our hands. And that is, we don't know. We call this just tension because the observed range overlaps the simulated range. So the next thing that needs to happen is we need to reduce the uncertainties in the reaction rates that are important to get a narrow distribution for the simulations in order to say there is a cosmological deuterium problem or there's no. And like this type of inference is impossible to do unless you have really reliable reaction rate uncertainties that you trust. And there are now, after we published this 3 years ago, but there are now laboratories that are trying to measure the important reaction is deuterium fusing with itself, D plus D. That hopefully will give us a reduced uncertainty in the reaction rate, which will translate in a reduced distribution here. So let's move on to stellar explosions. This is an artist's impression of a classical nova. A classical nova occurs when you have a compact object, a white dwarf, that accretes matter from a companion star. This can be a main sequence star. And then the matter is accreted on the surface of the white dwarf. And then the temperature increases in the accretion disk up to the point where nuclear reactions occur. We call this a thermonuclear runaway, and then energy is released in an explosive manner. Matter is ejected into space, and then these are actual images of classical novae. Nova Kidney, 1992, very famously. It has the double star system in the middle here, and then this nice ring. Resolution is really poor. This image has done a lot of damage to my understanding of novae. I always thought, oh, it's a nice ring and there's a central object. And it's not like that. The resolution is poor. With better resolution, you would observe images like that, where you see a clumpy appearance. And this clumpy appearance is very important. We know that novae are prolific dust producers, but there are so many open questions related to these classical novae. Classical novae eject about 10 times as much matter as we predict in simulations, for example. That's a big problem. So a long time ago, 2006, I teamed up with Jordi Jose, I mentioned before, and Margarita Hernans, also at Barcelona, and we wrote a review on the nuclear physics in classical novae. And I wrote the nuclear part, and I made a prediction, which I proudly show here, which turned out to be correct. I've made many predictions that turned out to be not correct. I will not talk about any of those. So this is the one that turned out. So what we said here, remember when I said in the supernova explosion, there are tens of thousands of reactions. Few of them are measured, but mostly you rely on nuclear theory. Classical novae are very different. Classical novae are the only stellar explosion where the nuclear physics is mainly based on experimental information. That's very important. So here is a result of a network calculation that we typically perform. This is now more complicated than Big Bang nucleosynthesis. You have number of protons again, so different elements in the y direction, number of neutrons, different isotopes in the x direction, and there's more going on. And then in train I would see the CNO cycles and would see an endpoint of the nucleosynthesis at sulfur 32 and so on. But I'm showing you this just to tell you that just in our laboratory, we have measured the reactions, nuclear reactions indicated by the red arrows, just in our laboratory. There are many other laboratories that also have measured other reactions for classical novae. So really, we have a lot of experimental information. We don't need to rely on nuclear theory. So, well, what can we say about these classical novae? So one thing we did after we performed all these measurements, we do the simulations, we asked the question, wouldn't it be nice to have a thermometer for this stellar explosion that we can predict the peak temperature during the explosion? And that's exactly what we did in this paper. That's now published 10 years ago, former graduate student of mine, Laurie Downen. And all you observe in novae, you have a light curve and you have the elemental abundances in the ejected shells. That's what you have. That's what you work with. And then we asked the question, okay, can we use observed abundances as nuclear thermometers? And we found that a lot of the observed abundances, they're not useful as thermometers, but the ratio of nitrogen over oxygen and sodium over aluminum were very sensitive thermometers. So now what we do, we compare our simulations with the observations. We try to match the peak temperature. And this only works because thermonuclear reaction rates are so sensitive to temperature. So remember what I told you earlier. The cross-section is very sensitive to energy because of quantum mechanical tunneling. And this is preserved, this dependence, once you do the integration to calculate the thermonuclear reaction rate, it's preserved as a very strong temperature dependence of the reaction rate. So what we did then, these are 5 different novae, and for this one here, we can precisely determine the peak temperature. This worked really well. For this other one, there's a larger error bar, but still we got the temperature out. And then there are 3 other novae for which we only determined upper limit. But this was the very first time anybody had predicted peak temperatures during an explosion. I mean, based on confronting simulations with the observations. And now, if you have a model of a stellar nova, you can even relate the peak temperature to the white dwarf mass. But this involves another step and another assumption. Then we thought, okay, this was kind of interesting. Can we come up with a method? Okay, this is a nuclear thermometer, but can we come up with a nuclear probe that tells us how much mixing there is? This mixing works like this. Okay, so you have mass accreted from the companion star onto the surface of the white dwarf. Then the thermonuclear runaway occurs, meaning the temperature is so hot in the plasma that nuclear reactions occur and then an explosion occurs. You see how these, I don't know if you can see this, but these white arrows, they sort of reach into the core of the white dwarf, meaning there must be mixing of the accreted burning layer with the underlying outer white dwarf layer. We know that because we observe a lot of carbon, nitrogen, oxygen overabundances in classical novae. This matter must come from the underlying white dwarf. This is very important. And then the explosion occurs and the ejecta are then emitted into space. Now, how much material is being mixed into the burning zone? The models don't make a prediction. So if you don't know, you assume 50%. 50% of the burning matter people have assumed is underlying white dwarf matter, and 50% is accreted matter from the companion star. So we did the same thing that we did here for the nuclear thermometers, but we look now at other elemental ratios that are observed to find a mixing meter. And this was another graduate student who worked with me in another paper we published 10 years ago. And this worked really well. And we found that it's 25% of the burning matter originate from the white dwarf. This is the first time people have quantified this. This was very important because this was 2013, around 2015 or 16, the first three-dimensional hydrodynamic simulations of classical novae appeared in the literature. And they also predict 25%. Now, they use our results to validate their calculations. The 3D hydro models are super complicated. And once you run them, you want to really make sure that that has some relationship to reality. So they said, okay, one nice thing is we agree with what these people predicted based on confronting their nucleosynthesis simulations to the observed abundances. So, okay, here, this is our laboratory. I will tell you a little bit. Triangle University's nuclear laboratory. We're a US Department of Energy Center of Excellence. What that means is they give us a lot of money. That means nothing else. 4 universities in North Carolina, they all close together, are part of this. And this is just part, it's on the campus of Duke University. Not all this is our lab, but there are different buildings that belong to our lab. So we are a relatively large lab for university-based laboratory. In this building here, we house, and so we have about 20 or 25 faculty who do nuclear physics research. I will only focus on nuclear astrophysics. There are people who do neutrinos and neutron electric dipole moment and nuclear structure. I will focus only on nuclear astrophysics. So in this building, there is a magnetic spectrograph. I told you, I mostly spoke about the nuclear reaction as it happens in the plasma, but sometimes you cannot measure it for complicated reasons. So now you need to resort to indirect measurements. You need to be clever, and you're not studying the nuclear reactions in the laboratory that occurs directly in the plasma, but you're doing indirect studies to populate the excited nuclear levels that are excited in the plasma. So for that, you need a spectrograph for these indirect measurements. So what it does, after nuclear reaction that now happens at much higher energy, you momentum select to the magnet the reaction products, and then you can electronically gauge on different neutrons and deuterons, and that way you can determine the cross sections. Then, there are very few of these spectrographs left. This was very big in the 1960s and 70s for nuclear structure, not for our field. But now there are very few left. And this is a specialized one that is dedicated to nuclear astrophysics. There's none left in the UK. There used to be 1 or 2 a long time ago. Then this is a unique facility, the free electron laser facility, and I can tell you more about it, but I cannot go into details. What this facility provides, it provides gamma ray beams, energy range between 1 MeV and 20 MeV, and they're monoenergetic. And you can use this gamma ray beam, you can have it incident on a sample that will excite nuclear levels. And again, you can study these astrophysically important levels indirectly. One of my graduate students does his thesis at this free electron laser facility. And this finally is yet in another building here is the Laboratory for Experimental Nuclear Astrophysics, LINA, where we measure these fusion reactions directly. And it consists of 2 ion accelerators. And the key here is people sometimes ask me, oh, so you go to CERN and Fermilab? And no, I don't know. It's exactly the opposite. In stars, stellar plasmas, the kinetic energies translate to relatively low kinetic energies, not the super high energies, low kinetic energies. But stars live a long time. So to measure these reactions, you need very high intensities of ion beams. That is the key here. So this accelerator here, the little one, produces the highest proton beam intensity in the world. That's what you need to build, otherwise you cannot compete in this field. And then here's some images of our graduate students. We don't have operators for that. You don't come in the morning, you say, hey, I want this. No, the graduate students, they have to operate these accelerators. They have to maintain the vacuum in the beam lines. They have to become experts in high voltage systems and electronics and radiation detectors and so on. When they finish, their CVs look really, really good. They have no trouble finding jobs. This is a measurement, a former student of mine. We published this in 2015, again, the S factor, not the cross-section. Cross-section drops. S factor versus bombarding energy. We measured these data points in red. We measured down to 160 kV, and our strongest competitors, they measured only up to 200 kV. Now, these competitors, this is a laboratory built in Gran Sasso, in Italy, underground. And the advantage they have, deep underground, they have much less background, because you need to pull out a small signal out of a big background. Deep underground, very few cosmic ray muons that can provide background. We don't have that advantage, but we have a much higher beam intensity, factor 10 more than they have. How am I doing with time, Mike? Yeah. Am I running out?
If you can finish up in the next 5.
Oh yeah, 5 minutes. Yeah. So yeah, this was done with 2 milliamp of beam. That will not tell you much, but our closest competitors have 200 microamp of beam, factor 10 less. So yeah, we'll finish with these type 1a supernovae. Here are examples. I already showed you Tycho supernova, and there are other famous historical type 1a supernovae. This is the last one that exploded in our galaxy. This should have been observed around 1900, was not observed, mainly because this was shrouded by dust and gas. And so the interesting thing about these type 1a supernovae, they have a very similar peak brightness. This is the light curve. So this is days, and this is absolute magnitude, the luminosity. And this shows you the light curve of different type 1a supernovae. And well, there is some big change here. This is a logarithmic scale, but notice the rate of decline correlates with the peak brightness. This is a very famous Phillips relationship. You can correct for that. If you correct for that, all these curves, they're lying on top of each other, and now you have something like a standard candle. Standard candle means these give all the same absolute magnitude. So if you then see the difference in the magnitude, that tells you, well, it must be because of difference in distance. Standard candle is very important. So most of the energy output comes from the decay of radioactive nickel-56 that's produced by nuclear reactions in these supernovae, and that decays. So in this is a famous image. It shows each data point stands for a type 1a supernova that was measured. So this is redshift on the x-axis, speed relative to us, and the magnitude, distance from us, on the y-axis. In the yellow region, this is where, if you have data here, that means the universe, the expansion of the universe is accelerating. And in the reddish area, the universe would be decelerating. And you notice that the data from these type 1a supernovae, they're slightly in the yellow range. And that was a huge deal, because this tells us that the universe, the expansion rate is increasing, is accelerating. And for that, Perlmutter, Schmidt, and Rees obtained the Nobel Prize in 2011. So I don't know if you are following this, but there are papers out there that say, wait a minute,
wait, this is super important, but this Phillips relationship, the way you do this correction for the rate of decline, this is all based on nearby supernovae. And this is obviously, if you want to study cosmology, supernovae that are very far away. How do we know that this Phillips relationship holds for type 1a supernovae that are so far away? Maybe the Phillips relationship changes with the age of the host galaxy of the supernovae, or with the metallicity, or with the star formation rate, and so on. These people, and there's some other groups too, they fit the type 1a supernova data without assuming any dark energy. This was the big prediction here. Oh, this is dark energy because the universe is accelerating. They say, no, we can just do the fit without dark energy. So I'm not saying here there's no dark energy. Dark energy, we have indications and proof of that from the cosmic microwave background radiation image that I showed you earlier. I'm just focusing here on, is the universe expansion rate accelerating or not? So for me, as an ignorant nuclear physicist, it's even much worse, because we don't even know what causes type 1a supernovae. There are two competing models. So one is a white dwarf that accretes matter from a companion star, and the other one, something completely different, is like colliding two white dwarfs, completely different. So if we don't know what the site of the type 1a supernova is, how are we so confident in this Phillips relationship, which is so important for cosmology? So this is where we came in, and we started a new project because we wanted to see if we can use nucleosynthesis in these events to make a distinction and find out, no, it's probably this side versus that side. This is the structure of the white dwarf in a type 1a supernova before it explodes. So it consists mainly of carbon and oxygen in the core, but it will have an outer helium layer. So, and we focus, the core will give nickel-56 for complicated nuclear physics reason. But the helium layer, when the shock goes through the helium layer, it may produce different nucleosynthesis depending on which side we're talking about. And this is interesting because these layers we probably can observe very early in the outburst with instruments like the James Webb Space Telescope. This shows a nucleosynthesis simulation. This is part of the thesis of one of my graduate students, Michelle Lee. This looks much more complicated than the one for classical novae, and more nuclear reactions. And this is a result of our Monte Carlo study. These are final abundances in a type 1a supernova explosion. And I mean, there are many, hundreds of papers that predict final abundances, but none of them will have error bars, because we derive these error bars again by using our probability density functions of reaction rates. This is very important because we can see, oh, titanium-44, which is radioactive, has a very large error bar. This is a logarithmic scale. And not only can we quantify the uncertainties, but we can also, for each isotope, we can pinpoint which nuclear reaction is the most important one by studying correlations in our simulations. So this, for example, is the one we really need to measure in the laboratory. This is how we motivate and justify measurements. Okay, my summary. To make fundamental discoveries, we need a strategic approach, advanced computational tools, world-class equipment. We really need to collaborate with the best stellar modelers, observers, and nuclear theorists. And then we want to take advantage of once-in-a-generation opportunities, such as the James Webb Space Telescope, or in nuclear physics, the facility for rare isotope beams. That's a $1 billion facility. I haven't talked much about that. This is my final slides. This is our laboratory. So we just got this one. This is a new accelerator we bought for $2 million. And this is a small machine, world record proton beams. And this one will cover the higher energy range so that we can cover from 2 MeV downwards all the astrophysically important reactions. Okay, thank you very much for listening to me.
So we've got a few minutes for questions. Yeah. So you know there's a Hubble tension because of the way Adam rays try to do the H0 calculation versus what you get from the CMD value for H0. Do you think the systematics that the group uses, the type 1 supernova measurement uses, is the systematics due to understanding of how the type 1 supernova happens, or which are the nuclear reactions that happen? Are those systematics significant enough that it can affect how they are measuring the value of H0 itself?
Yeah, so the systematics, I think, has nothing to do with the way they do the analysis of the uncertain nuclear physics, but the nuclear physics comes on top of that. I would argue that if you don't know what the site is, how can you apply this Phillips relationship that derives from a nearby supernovae? This is what I'm very concerned about. Yeah, as you say, I mean, there's a Hubble tension and there's a lot going on. But I think people have not appreciated the nuclear physics uncertainty, what I sort of talked about much, because very few people are experts in that.
I mean, it's just the curve that you would be worried about if we are doing the curve analysis, the light curve analysis correctly, without understanding the nuclear physics.
Yeah.
One more question.
Yeah.
What's the most likely solution for the lithium problem?
Oh no, I don't know. I'm an ignorant nuclear physicist, so I just made sure I'm pretty convinced it's not nuclear physics. But as you know, there are people, they say the observations must be wrong because lithium observations are really, really difficult. Lithium is being destroyed at already 1 million Kelvin. So you really need to make sure that you look very far away, the stars, you observe the lithium in their atmospheres, that the stars have not destroyed any lithium. So a lot of people say the problem is in the observations. But there are people who do this for a living. And they say, no, there's nothing wrong with the observations. There must be something wrong with the stellar models because you guys, stellar models, you don't understand convection. And so nobody knows. And then, of course, there are probably hundreds of papers written on non-standard solutions, physics beyond the standard model. And I cannot follow all of those papers. So nobody really knows.
Could it be something simple that the temperature of the universe changes the time slightly differently?
Well, but that's a non-standard. Yeah, so it could be something like that. I mean, people have looked at the variation of universal constants with time and stuff like that. And sometimes you do get some solutions, but then it's too much tweaking here and there to make things fit. So overall, we really don't know.
Thank you. We're about time by chat.
Yeah, I think we've got to give up the room soon. Sean Ryan says, in the past, it used to be noted that S-factor measurements could be missing resonances in the energy range of astrophysical relevance, so S-factors could be underestimated. Given this current state of measurements, is this still a concern?
No, this is not, because this was important for solar physics, solar reactions, but these reactions that I showed you in Big Bang nucleosynthesis, they're all non-resonant. There's no resonance that plays a role there. It's the only astrophysical site where resonance really do not play a role. So, okay. I mean, there are some, I don't know how much details Sean knows. There's some other reactions, some nuclear physicists still think this exotic nuclear reaction, beryllium-7 DP, that may solve, but this is sort of a long shot. And there is a resonance involved there, but I don't think so.